start by reminding you that we talked about last time, we talked about how the site was chosen. And I told you the little story about Senator McKellar and how those political kind of decisions get made. And I don't want to take away from that, because that's kind of the way things happen. And as you look back on it from a historian's perspective, you'll pull out those key little things that will stick in people's mind. And that's what's happened there. When you look at the reality of what happened all during 1942, there were people coming to this area, talking with the Tennessee Valley Authority, and looking at various landscapes around this area. And they were here in the summer. They took the tours through what's now Oak Ridge, and they covered other places in Tennessee. But one of the main drivers for choosing this location literally was the fact that the Norris Dam had just been built in 1936, and they actually had a power line that ran to the south and to the west. And TVA said to them, look, if you'll put that within 5 miles of that power line, we'll supply the energy for you. Now, as I mentioned, I think last time, Norris Dam wasn't nearly productive enough, didn't produce nearly enough energy to do what was needed in Oak Ridge. So they had to literally built 6 more dams. Fontana Dam was built just to supply electricity to Oak Ridge. Enormous amount of electricity. Now, one of the things that they provided that electricity for were these 1,152 calutrons. Remember I told you it was named for California University cyclotron, and Ernest Lawrence is the one that invented that. He's a Nobel Prize winner, and he was working on a cyclotron, which is a calutron just takes a piece of what a cyclotron would do. A cyclotron would have it running in a complete circle, and the calutron just stops it at the top and pulls that material out. Now, one of the things that makes this so reliable is the fact that there's no moving parts, and that Lawrence was able to convince General Groves that he could produce this uranium-235. Remember I told you that you needed in 1,000 pounds of uranium ore, you needed that 7 pounds of 235. You need that to produce the material for the atomic bomb or for a fission reaction. And that not moving any parts and being able to just put this in the right place to pick out that little bit of 235 is what Lawrence was able to convince Groves that could be done. So that's why those are 1,152 of them in 9 large buildings, largest magnets in the world at the time. And that was what was drawing the majority of the electricity early on. Then the K25 site, the gaseous diffusion process, which was a continuous operation that used about 3,000 stages in one building. The one building being a U-shaped building that was a mile from one end of the U to the other. And those 3,000 stages each had motors on them to run a pump to pump that material as a gas through a porous membrane that the 235 would go through a little easier and a little quicker than the 238. So you could, if you continued to do that, you would begin to accumulate a larger percentage of 235. But those also used a lot of electricity. So by 1945, there are people who have actually tried to study this and say how much electricity was being used by Oak Ridge in 1945. There's all kinds of numbers out there. Give me a guess. What would you think as a percentage of what was being used in the entire United States? How much would have been used in Oak Ridge? Yeah, you'll read those kinds of numbers. That's actually too high. It wasn't that much. But it was at least as much as the whole city of New York City. And there are some reports that will call it as high as a 10th. I'm not sure that any of those numbers can actually be proven. Right, right. It would have been about right. But at any rate, a large amount of electricity being used to drive these Caleutrons. So let's go to the next slide. Now, as the construction started, what you're looking at there is the construction at Y12 in Bear Creek Valley. And remember, the valleys are down here and the ridges, up on top of the ridges, the whole area is laid out that way, ridges and valleys, so that they thought the flat part that could be used would be the valley floors. And I mentioned that 3,000 people had to leave on very short notice to make room for this construction. And don't you know that was amazing? I have had people tell me that actually lived here during that time as small children or as youngsters. And what they would do, they had to move away, but what they would do is they would walk back up on the ridge tops and look over and see the construction activity. Don't you know it was amazing for these people here in East Tennessee to see all of this large equipment coming in, moving dirt and building, literally thousands of people building, tens of thousands of people building things in 3 different valleys all at once. Okay, Lee. This is the first building, the Alpha 1 building. It was started at Y12 on February the 18th, 1943. And that was now I said Alpha. There's 2 stages to these Caleutrons. Alphas stood about 20 feet tall, and the first of those were arranged in oval shapes. That's why they called it a racetrack. Give me the next slide quick. I think that's where it is. Yes. The racetrack is because of the oval shape. Now, the electricity would have been on all of these magnets, but don't make the mistake of thinking, oh, okay, the uranium must have gone around the racetrack. No, the uranium was in batch processes between the magnets. It would go in at the bottom and come out at the top. Remember that little diagram I showed you? And that's how the Caleutrons batch processes. There would have been 96 of them in this one arrangement. And these are alphas, so they would have been in Alpha 1, Alpha 2, or Alpha 3. Now, in Alpha 4 and 5, they didn't make them in the oval shapes because the ovals didn't really work well out here in the sharp bends. It was not as productive, so they put them in rectangular shapes for Alpha 4 and Alpha 5. And then there were 4 beta buildings, and the beta Caleutrons were smaller. They were about 10 feet tall, and they were the ones that could actually take it and enrich it or separate it up to the weapons grade level. And actually, the beta Caleutrons continued to operate at Y12 until 1998. And they continued to separate all of the elements in the periodic table into the isotopes for those elements, some of which went over to the graphite reactor. And we'll talk about that as well, in that it was built to prove you could produce plutonium in a uranium reactor. But they didn't use that reactor for that. They went out to Hanford, Washington, and built them out there, as we mentioned. But this reactor is still sitting here, and it's capable of being used for things other than to produce plutonium. So they began to use it to produce other isotopes, some of which were used for medical purposes. Now, back to the Caleutrons for just one more story about these Calutron girls. These young ladies right out of high school that came here and operated. We talked about Gladys Owens last week. Another story about them is when Tennessee Eastman is the company that was operating Y12, General Groves went to several different large companies and leaned on them pretty heavily on their patriotic duty to help in the war effort. DuPont was one, Stone and Webster, he got to actually build the Y12 site, building the facilities, and they built Oak Ridge, the city of Oak Ridge. And then there was DuPont that was working over on the graphite reactor, and then J.A. Jones was a construction company for the K-25 plant, but he would go to any of these large companies. He went to Tennessee Eastman because they were able to manage large operations, and he needed folks who could do that and do it well. So that's why he leaned on them to actually contribute to the war effort by coming and managing these plants. Tennessee Eastman took the Y-12 plant, and of course they couldn't hire enough young men, nor could they hire enough technically qualified people to run 1,152 of these Calutrons. So they created a training program, and they went to high schools, and they started focusing on young girls in high school because they wouldn't be taken off into the war, if you will. They wouldn't be into the military. They'd be available. And they developed this training program and started training them. And the people from out at Berkeley, California, where Lawrence was, kept saying to them, look, we're in a race with Germany. We need to be as productive as we can be with these Calutrons. You need to put scientists and engineers on them, not those young girls. Well, Tennessee Eastman couldn't hire enough scientists and engineers anyway, so they said, look, we'll run a contest. We'll put our young girls on one bank, and you put your scientists and engineers on the other. We'll let them run a week, and we'll see who's most productive. Well, you know what happened. At the end of the week, the young girls had beat them hands down because they were practicing statistical process control. But they didn't know that. They just knew that they'd been told to keep that meter on a certain spot. And if it drifted to a control point, a number they'd been given, they were to adjust the knob and bring it back. Now, they didn't know what they were doing, but they knew they were keeping it on that one spot. Now, the scientists and engineers, on the other hand, they knew enough about the system to know that, hey, when this meter starts drifting, there's something causing that. So I'm going to go out and fix whatever it is that's causing that to drift. And they never could get it to operate. So finally, they went away and let Tennessee Eastman alone, let them hire these young girls, train them, and actually run them to run these Calutrons. And they did it 3 shifts a day, an 8-hour shift. And what they were doing is they were sitting there keeping a meter on a certain spot by turning it one way or the other. Now, I asked Gladys what she thought she was doing, and I told you the bobby pin story last time, so I won't repeat that. But she did not know. She knew she was doing something to help win the war, but she didn't know what. And she was very proud when she came back that she had been part of winning that war. Okay, let's go to the next. So that's the Hanford Works that we talked about, the 3 reactors that were built out there, and they were built along the Columbia River, and they were built because of the water supply that was there. They used water for coolant, whereas the graphite reactor here in Oak Ridge is an air-cooled reactor. All right. So the reason that they went to out to Los Alamos, they didn't want to put all of their eggs in one basket here in Oak Ridge. If they built all those reactors, they wouldn't really have room for it. And that's why they went out to Hanford and built the reactors there. Now, just like the Senator McKellar story about Oak Ridge, there's a Los Alamos story. And I'm almost confident that this is exactly how it happened. When they were talking about where to put this thing, Oppenheimer had vacationed up on that plateau where that boys' school was, and he knew about it. And he's the one that suggested to Groves, that's where we could put that laboratory. Now, it met the criteria that they were looking for, and so they actually took that site and made Los Alamos. If you look at that area on a map, there's a large volcano up at the top, and it just looks like fingers where the lava flow has run out over the years. And Los Alamos is sitting up on one of those lava flows with the canyons down on either side of Lee, anything you'd add to that about the Ranch School or Los Alamos? Right.
So you need another laboratory for design and testing of the weapon. That was personal of Los Alamos. Somewhere else from Oak Ridge, I guess, for espionage purposes. And so Los Alamos was chosen, and there is the site of the school.
So I've been out there a number of times, and that school is still there. That actual building that you're looking at there is still being used. There's a little history center that's Fuller Lodge is the name of the building that's still there. I'm saying it's this one. I could be wrong. I'm not sure that's the case. But Fuller Lodge, built with those logs like that, is still there and being used today. So we'll end this section, Lee, by talking about the two bombs that were dropped on, one on Hiroshima and one on Nagasaki. The little boy bomb was dropped on August the 6th, 1945, and on the Hiroshima. And the damage done, there are numbers that vary, and I think 70,000 is a good number. Sometimes you'll see over 100,000. But you can also see pictures that were taken when they went in, and you can see images of the damage that was done and the horrible effects. I mean, many of those 70,000 or whatever the number was were just immediately vaporized, just nothing left. Others out on the periphery had burns, radiation sickness, horrible results of that explosion. And then on the 9th, the Fat Man was dropped on Nagasaki. One interesting concept about why these two places were chosen, they were deciding which cities to use as targets, and they wanted them to have some military involvement in the cities. And they had a list of the names of cities that could be potential targets. One of them was Kyoto, and it was taken off the list by Stimson, who was the Secretary of War at the time, and he took it off because of the significance of the city to the history of Japan and its culture. But he left Hiroshima and Nagasaki on the list. Nagasaki was not the first intended target for the second bombing, but the first city, now I've forgotten the name of it now, it was overcast and they couldn't see it, so they went to their second choice, which is Nagasaki. I've read about one individual that happened to be in both cities. He was on the first explosion in Hiroshima, and then he went to Nagasaki. 3 days later, they dropped it there. He was in the outskirts of both cities at both times, but he literally was there for both explosions. Yes, please. He did. Stimson knew about it. He was a part of the S1 committee, the uranium committee that President Roosevelt formed. As a result of the Einstein letter that actually Szilard wrote the letter for Einstein. Well, they wrote it together, okay. Einstein signed it because they needed a name that they thought the president would listen to. And they went and actually got the letter to the president through an industrialist. I want to say his name was Alexander, Sachs, I believe, Sachs. I think that's the correct one. And they used him to get the letter to the president. And then the president formed the committee. Stimson was on the committee and was very much in charge. Now, you remember the vice president didn't know anything about it. Yeah, Truman didn't. They didn't share it with him. There was just a very few people that actually knew what was going on, and yes, Stimson. Now Stimson actually came to Oak Ridge. He was the. They thought Roosevelt was coming, but he died. But Secretary of War Stimson did visit Oak Ridge.
Also, Stimson, I read, had spent his honeymoon in Kyoto when he got married. Stimson had honeymoon in Kyoto in the 30s when he got married and knew how beautiful and historic Kyoto was. So he made sure that Kyoto was off the list. Because most cities were being firebombed in Japan.
Tokyo.
Yeah, just devastated by firebombing, conventional weapons. But they wanted to keep a couple of cities virgin, so to speak, so that when the atomic bomb got developed, you could drop on a city that hadn't been touched and really demonstrate the power of an atomic bomb. And Kyoto was on that list, but then Stimson took it off because he knew how beautiful and historic the city was.
Yes, please. Unfortunately, there's all kinds of second guessing of that situation, and you can even go further and find all kinds of opinions from historians about the bombs didn't have anything to do with ending the war, Russia coming in, why the war, all kinds of suppositions. Now, going back to the use of the bomb, this is Ray's personal opinion. I won't base it on anything. But in my reading and my research, I see that had been set in motion by Stimson and by the core team, the committee, the S1 committee working on that. Roosevelt gave his approval, agreed to support it financially, and never involved himself further in it. But he set it in motion, knowing exactly what it was being built for. I don't think he would have hesitated a minute to use it, just like Truman. And again, there's a book written about his most difficult decision, where he writes about that decision. And of course, hindsight, he supported his decision 100%. Now, how much of it he actually made, I'm not sure. I think the military was moving right along a pre-prescribed path, and they didn't stop and say, what do you think? What do you think? Now, remember, there were a large number of scientists involved in the project that created a letter. A lot of them signed it and said, you know, we know what we've created. Do a demonstration. Don't drop it for real. And that didn't get considered. Oppenheimer did, yes. Alvin Weinberg was a part of the letter in Oak Ridge getting it done. And you have to remember, this first time anything so powerful had ever been seen. And you've got to know that those people who were intimately involved with it had to say, oh my, you know, I writing it on paper and figuring it out and saying, you know, X times is going to be big, but being out there in Trinity or after the effects, I'll tell you, just to give you a little more insight, when we formed the Manhattan Project National Historical Park, formed in 2015, a group of us gathered in Washington, D.C. It was a scholars roundtable, and there were 20 of us there. There were 2 Japanese, and they were a part of the group of 20. And what we were deciding is what are the major themes that the national park will emphasize when you put a park together to talk about the Manhattan Project. We wanted to be sure that the entire story is included, not just glorified or grandiose about what the United States did. No, we want to talk about the involvement by the British. We want to talk about all of the aspects of it. And the Japanese input was be sure that you include that we would want to never do it again. Now, let me tell you one more story, and then I'll give it back to you. I talked about these Calutron girls. We call them Calutron girls now. They were cubicle operators back then. And there are only a few of them left now. One is Ruth Huddleston. Ruth is my go-to Calutron girl. When somebody comes to Oak Ridge or somebody asks, I want to talk to a Calutron girl, I get Ruth. The NNSA, National Nuclear Security Administration administrator, came to Oak Ridge a few weeks ago, and all of these people up at the top of DOE, now when they come to Oak Ridge, they want to meet a Calutron girl. So Ruth is the person I take to them, and we did that. Sat with her, sat with the new Lisa. I can't think, her last name is Dash, but I can't remember what it is. Charity. Sat down with her, and I asked Ruth the question I always ask her: what did you think you were doing? And she will tell you, I didn't know. I knew I was helping to win the war. And then I'll say, okay, Ruth, when you found out what you were doing, when they dropped the bomb and it was in the newspapers, what did you think then? And she will say, I was proud to be a part of helping to end the war because my boyfriend was in Germany and I already knew he was going to have to go to Japan. But she said the next day I saw in the paper and heard on the radio how many people we had killed. And it really depressed her. She went for a week without being able to sleep just because she had been a part of killing so many people. Now, the administrator of the National Nuclear Security Administration got up right close to Ruth and said, let me tell you why I understand how you feel. And she said, my job, let me tell you about my job, is to be sure that all of the nation's nuclear weapons are capable of being used. And if the president wants to use one of them, it'll work. And I hope that we never have to use it. Now, that gives you a little insight into the people who were actually involved in producing that weapon that killed those 70,000 people, and more died later. But it also gives you insight into how we want to never, ever use nuclear weapons again. We'd love to be a world without them. But as long as anybody's got them, we're going to have the biggest and the most.
Thank you, Ray. Any questions for Ray while I put up a different file here?
Yes. Okay, let me help her with that. I was talking about a cyclotron making a circle, and I was talking about the Calutron. You have a half of a circle. Now, the uranium, it's a uranium chloride mixture. It's put in at the bottom, and it's attracted out into a vacuum chamber electrically because it's a positively charged ion, and it's just moving out because of that electrical charge. But the two magnets on either side, that magnetic field causes that ion to bend. And when it bends, the centrifugal force will make the 238 make a slightly larger arc than the 235. So that's what's spinning, is the actual uranium. Yeah, the actual material. Mm-hmm. Yeah.
Thank you, Ray. There's nobody in Tennessee or expect in the country that knows much about the history of the Manhattan Project as Ray Smith. So it's great to have him be part of this. Of course, we didn't get to the Manhattan Project directly. And that's what I want to focus on for a while in this course. When the 20th century started, the atom was the smallest piece of matter. And in 1900, that's a long way from 1939, 1945. A huge number of discoveries, primarily in physics, occurred in the first half of the 20th century that led to the Manhattan Project, that enabled the Manhattan Project. And it's such an interesting story to me because it's also the time when there were so many bad events going on in the world. The Great War, World War I, Hitler, and then World War II. And so here are some of the people we want to talk about in that historical progression. See, only when you get to here are you near the point of the Manhattan Project. But I want to start talking about the turn of the century. Radioactivity was not understood in around 1895. The electron was only discovered in 1897. Einstein came along, made crucial contributions, E equals mc squared, which is a critical part of why you get so much energy when you split uranium into two pieces. Rutherford, the British, well, actually he was from New Zealand, he worked at Manchester, discovered that most of the mass of the atom is in the nucleus. A shocking idea. So on and so forth. And finally then you come to Heisenberg. Heisenberg was the Oppenheimer in the German war effort. Heisenberg was a Nobel laureate nuclear physicist. And Bohr, the great Danish Nobel laureate, was his mentor. Sometime in this semester, we want to talk about Copenhagen, the play. The meeting between Heisenberg and Bohr while the Germans were occupying Denmark. Anyway, it was not until 1932 when the neutron was discovered. And then things started happening very rapidly that led within 10 years to using the neutron and to make nuclear fission happen. So I want to tell you something about that. This is not a science course, but I want to tell you some of the, at a high level, some of the science involved in each of those discoveries that led to the Manhattan Project and the atomic bomb. At the same time, the world was coming apart. The Great War, World War I, raged for 4 years. And I'll tell you more of these stories. Marie Curie her career was interrupted. She did X-ray machines of people, of the many people wounded in World War I, a brutal war. Germany was left in a very weak state after World War I. That was one of the factors, I guess, that contributed to Hitler coming to power. He became Chancellor of Germany in 1933, right away passed his first set of laws that resulted in Jewish public servants being removed from their jobs. That led to the exodus of the great Jewish German scientists out of Germany. In such ironic manner, they contributed so greatly to the US war effort because Hitler had driven them out of Germany because they were Jewish. Of course, the Germans invaded Poland in 1939. That started World War II. Britain and France declared war. A war in Manchuria started by the Japanese, so on and so forth. That then resulted in the Manhattan Project and ending. Germany surrendered in spring of 45. Finally, after the atomic bombs were dropped on Japan, they surrendered in September of 45, and that ended World War II. And so it was a time of great science discoveries, but also the world coming apart. And so these are some of the discoveries I want to talk about, march through these quickly to give you a feel for how these discoveries led to the science that enabled understanding nuclear fission and using it to make a weapon. First was X-rays. Wilhelm Röntgen was a German physicist, and he was doing experiments with tubes, evacuated tubes. And here is a picture. You know, he was doing experiments with an evacuated tube, and you had a cathode and anode. You you ran a current through a filament, and he did not understand it, but it produced a flow, a current, something that was detected by the anode. And you would have a primitive crude vacuum in the glass tube, and that something would flow from the cathode to the anode. Well, now we know it's electrons flowing, but the electron has not been discovered yet. So Roentgen was doing experiments with trying to improve that flow, whatever was going on in 1896. And he found that there was something that penetrated out of the glass tube. He did not understand it. They were called cathode rays, something when there was a flow from the cathode to the anode. But then they found that these rays were penetrating. He surrounded the glass tube by a black blanket, and found that whatever was coming from these glass tubes even penetrated the black curtain around the glass tube and illuminated a screen behind. And so it was a very penetrating ray. He didn't know what it was, so he called it an X-ray, because he didn't know. And so he was the first to find out that when things were flowing, you were making a very penetrating radiation, so penetrating, he found by accident, that if he put his hand in front of the screen, that you could see the bones in his hand. The X-rays, whatever they were, penetrated the skin, but got absorbed by the bones in the hand. And actually, his wife was the first one. He said, "Put your hand there," and so there's that famous picture of I think that's her hand with the wedding ring on, her left hand. And so these X-rays could penetrate skin and show the bone structure. Well, that was a sensation that people then verified, known around the world. An enterprising firm in London advertised lead-lined dresses, so in the Victorian era, that ladies could be sure that they weren't being penetrated by X-rays to show their undergarments. So this was the first big sensation, first big breakthrough. The Nobel Prize was invented in 1901, and Wilhelm Röntgen won the first Nobel Prize. Turns out that Röntgen had relatives in Iowa, so he intended to move to Iowa, but then World War I came along, and there was no way to leave Germany then. And of course, that, in some ways, he's considered the father, Röntgen is, of diagnostic radiology, because now we use X-rays in such a common way in medical diagnostics. Indeed, element 111 is named after Röntgen. Yeah. Not so much, no. Now the ones I'll talk about in a moment did affect people, but not so much for Röntgen. Marie Curie died of cancer-related things because of all the radioactivity. But Röntgen lived to be, I think, in his late 70s. So he was not affected much. About the same time, J.J. Thomson in England, in Cambridge, was doing experiments on cathode ray tubes. He built a cathode ray tube just like Röntgen had done. And he was trying to figure out, what is it that flows from the cathode to the anode? What is it that was producing those X-rays that Röntgen found in Germany? Well, he got a better vacuum in the tube, put plates in here. Let's see, will this work? I just loaded this up. Oh yeah. So he flipped the charge on those plates, positive, negative, and he saw that beam or whatever it was deflected. Therefore, whatever that was had electric charge. He was the first to figure that out. That mysterious flow from the cathode anode had a charge. And then he mounted a magnet around there, and he measured the charge to mass ratio of whatever it was that was flowing from the cathode to the anode. And you know, it was assumed that if there was something floating, it'd just be a hydrogen, ionized hydrogen nucleus, element number 1. But what he found was that this thing was a lot lighter. It was 1,800 times lighter than a hydrogen ion. And so that was the electron. So Thomson then discovered the electron by that experiment. So that was a big deal. You see, so he knew now that the atom was not indivisible, that electrons were components of atoms, and electrons were light. They were 1,800 times less than the mass of a hydrogen or helium atom. So very light things. So there must be a whole lot of these electrons. So it was assumed that the atom would be like a plum pudding. It was called a plum pudding model, where you'd have a mass of positive charge, because the atom had to be neutral, and then little raisins, electrons stuck around the different places in the atom, the plum pudding model. And that's why you got neutrality, the negative electrons stuck all around this positive, evenly distributed positive charge. And that's what an atom was. So this is a big deal. He got the Nobel Prize in 1906 because he found the first subatomic particle. Well, J.J. Thomson was also a good mentor and teacher. Indeed, Ernst Rutherford, I'll tell you about, the father of the nucleus, was his student. And Ernst Rutherford from New Zealand succeeded J.J. Thomson as head of the Cavendish Lab at Manchester. 6 of his research assistants in J.J. Thomson's lab won Nobel Prizes in physics, and 2 won Nobel Prizes in chemistry from his group. His son won a Nobel Prize in 1937 for figuring out that an electron also had wave-like properties, the electron that his father had discovered. So that was a big step forward to the discovery of the electron. Becquerel. We did a German, Röntgen, British guy, Thomson, and now an elegant Frenchman. Henri Becquerel lived in Paris. He was from a wealthy family. Indeed, he was third of 4 generations of physicists in France, working in Paris. He was studying photofluorescence. You know, there are some elements. Mark's a chemist, he would know all about this. You shine light on some materials and it fluoresces. It gives off light when you turn the lights off. You know, watches used to have dials of fluorescent material so you could see them in the dark. Maybe Ray still does. You don't have a digital watch? Oh, God. Oh, you're old-fashioned. And so that's photofluorescence, where light is absorbed and then it excites the atom, excites the levels in the atom, and then the electrons jump back down and give off light of different wavelengths. So that's what Becquerel was studying. He heard about Röntgen's discovery that there were these X-rays that came off when you ran a current through a cathode ray tube. So he tried the experiment with uranium salt. He knew that salts of uranium would fluoresce. You expose them to sunlight, and then he would put them by photographic plates when he took them out of the sun, and he could see the fluorescence, the light given off. Well, he was trying to see if they would also give off X-rays, uranium salt. And he was trying to do the experiment where he was working on fluorescence, expose the uranium salt to sunlight, and then take them out of sunlight, put them between photographic plates, and then they would expose the plate, and you can see the image. That's fluorescence. But it was there was no sun in Paris for some weeks, so he put this package of uranium salt between photographic plates, just threw it in the drawer of his desk for a couple of weeks, and then took it out a couple weeks later and thought, well, I'll expose that film. And he was shocked to see that there was an exposure there. that there had been no direct sunlight on uranium salt, but somehow something was coming off. There was an internal source of energy. It was not photofluorescence. It was internal fluorescence. Something in the uranium was giving off its own radiation independent of X-rays being generated by the cathode ray tube like Röntgen, or independent of the sun shining on the uranium salts. Well, now we know it's radioactivity. He discovered radioactivity. He did not understand it. He got the Nobel Prize in 1903 along with Marie Curie and Pierre Curie that I'll tell you about for the discovery of radioactivity. Now, he suffered damage because in succeeding years, you know, they isolated radium. Marie and Pierre Curie isolated radium, and he was doing experiments on radium. And so he put those samples in his vest pocket of his sports coat, and he later had burns on his skin because of radioactivity, the natural radioactivity given off from radium. And so he died at age 55, Becquerel did, because of skin cancer, people think. So yes, there were deaths because people didn't understand the harmful effect of radiation on human cells. Marie Curie, what a story. Polish, grew up in Poland, from a elegant family. I should try to move this box here. Oh, well, you can still see it. This is Marie Curie and her sister, older sister, and her mother and father. It was a well-to-do family. You know, Poland was part of Russia, the Russian Empire at this time in 1867. Parents were prominent teachers. Her father taught science and math. They had some wealth, but then they lost their wealth because the parents became involved in the national uprisings to try and win Poland's independence from Russia. Of course, Poland's tried to do that any number of times throughout its history, and they never succeed for very long. So they lost their fortune. And I just make this comment here because this comes back later. Maria's father was Maria at that time. She was named. She later became Marie. Her father was an atheist. Her mother was a devout Catholic. So there's a religious difference that then affected Marie Curie later, had an impact on her life. They put together money for her older sister to go to Paris to study medicine, but Maria couldn't go. You know, she didn't have money to go to college. Women in Poland were not allowed to go to college. She kind of went to college on the sly to try and learn about science, learn from her father. And she went to work as a governess to support the family and to send money to her sister, being older, that went to Paris to study medicine. A family that she was a governess for had a boy about her age, I guess Marie Curie, or Slodowska, Maria Slodowska, was probably in her late teens, early 20s by this time. She fell in love with him. They wanted to marry, but his parents would not let him marry her because they had money and her family did not. And so that really destroyed Maria Slodowska. She then worked some more, saved up money, and went to join her sister finally in Paris, stayed with her sister for a while. Her sister was now married by this time, moved into a dungy one-room place in a basement, no heat, very little money, often near starvation. But she managed to study physics at the Sorbonne. She got her physics degree in 1893. She met Pierre Curie, and they married in 1895. He was he already had finished his physics degree. He was working at the University of Paris. And she wanted then to go back to Poland to teach since she got her undergraduate physics degree. Pierre said, okay, I'll go with you. I'll go and I'll just go there and I'll give up my science career. I'll go with you and I'll teach French in Poland. So Marie Curie went back to Poland She had her degree from a prestigious institution in Paris, in France, but Krakow University wouldn't hire her because she was a woman. So that didn't work. So they came back to Paris. She started working on her PhD. She worked further on Becquerel's discovery of 1896 about radioactivity. They did experiments on understanding the radioactivity. They knew that Becquerel had figured out that uranium gave off its own internal radiation. And Marie Curie set out for her PhD work to study two uranium minerals, pitchblende and torbernite. And they also had natural radioactivity. Try and understand what is it in those minerals that was giving off an internal source of radiation. This is Pierre, that's Marie. They had, the first daughter was Irene. She also won a Nobel Prize. This Curie family produced 5 Nobel Prizes. Then she had a second daughter, Eve. But Pierre Curie had invented an electrometer before he married Marie, and that was just a way that you could measure the ionization. You know, how would you measure the level of radiation given off by these minerals? Well, the radiation would come off and ionize air around the sample, and you could measure that amount of charge from ionizing air around the quartz tube from that penetrating radiation. And that was the measure then through Pierre Curie's electrometer. And so there's a picture of their lab of how they measured the amount of activity in different minerals. Well, this was hard work. They discovered 2 elements in the process. They started with tons of pitchblende, doing chemical separations. By April, the 2 Curies working together, very painstaking work doing chemical separations on, starting with tons of pitchblende to keep separating out chemically and find out what is it that's emitting this internal radiation. Finally, in 1898, in April, they weighed out a 100-gram sample of pitchblende, and they figured out that they had found the element. They had isolated the source of the radiation there. And so that was the element they found. They called it polonium in honor of Poland. Polonium is element 84. And so that's the first element. So in December of 1898, they announced, in July, they announced discovery of one element, polonium, and then they kept working on pitchblende and found a second element they called radium, because the radiation gave off very hard separations, starting with a lot of material, all chemical separations. The polonium was not so bad because it resembles bismuth chemically, and there was no bismuth in the pitchblende. Polonium was, but radium was more difficult because it's chemically similar to barium, and pitchblende contains barium also. And so it was a lot of work. So from a ton of pitchblende, they separated 0.1 gram of radium chloride in 1902 and got a Nobel Prize also for discovering element radium, which is element 88. So Marie Curie shared in 2 Nobel Prizes, one with Becquerel for discovery of radioactivity, and then with Pierre, her husband, for the discovery of 2 elements, polonium and radium. And indeed, element 96 is named curium in the honor of the Curies. Her personal life took a hit when Pierre went on the Rue Dauphine one day in 1906. It was raining. He got hit by a horse-drawn carriage. His skull was crushed. He was thinking and not watching. And so Pierre died suddenly in 1906. And you know, he was a professor at the University of Paris. They had won 2 Nobel Prizes by the time she had. Only then, because he died, did the University of Paris reluctantly make her the professor at the University of Paris. I'll tell you more of the story next time, but because she was a woman, there was a lot of opportunities that were not afforded to her. And so she's the first to win 2 Nobel Prizes. She's the only woman to win Nobel Prizes in 2 different fields. The first person to win Nobel Prizes in 2 different areas, physics and chemistry. But she was never elected to the French Academy of Sciences because she was a woman.